Hello there and welcome to this video which is all about pressure in liquids. Now I'm hoping that if you're watching this video you've kind of seen and processed the kind of demonstration that you can see on the screen, okay, which is that when you take, for example, a cylinder of water and put some holes in it, that what you find is that when the water shoots out it comes at different covers different distances depending on the depth of the liquid. You notice the deeper we go, the further the water lands from the base of the cylinder. Okay, now this is a really nice demonstration of pressure in liquids, and what we're going to do is we're going to follow some quite sort of difficult steps. It's quite tricky, this one, to try and prove why this is the case. Okay, now thinking about pressure, let's get the kind of qualitative bit out of the way. You can see, hopefully from this demonstration, that the pressure is greater the deeper we go. That jet down at the bottom is traveling a greater distance than the one up at the top. And so therefore what we can say is the pressure is increasing with depth. And that is our goal today. Okay. To do this, we're firstly going to model our cylinder in this sort of classic way as having an area H and a height or depth H. Okay, it's a bit, sometimes students get a bit confused, indeed I get quite confused about this use of H, although it's a standard number. Okay, generally the higher that column, the deeper we are going. Okay, and we're going to think about the pressure at the bottom of that column of water. All right, now to do this, we need some equations. And these are ones that I'm going to hope that you know already. Certainly if you're in my classes, you should have met most of these. Okay, and what I want you to do is try and do a bit of recall. We'll try and get these equations down and then see how they combine to produce something that will then explain what we see in this experiment. So let's go for it. First equation that we need is an equation linking pressure, force, and area. So what I'd like you to do at this stage is to pause the video, try and find an equation linking pressure, force, and area, and then when you're ready to go, just play, and you'll see if it agrees with what you've written down. Okay, hopefully you've got that written down. The equation I was looking there was our P equal to F divided by A. Pressure was the ratio of force to area. Notice I put a number 1 there. You might want to do this in your equations because you're going to use this equation and sort of modify it to make a new equation for the pressure in the liquid. So, next step is to find another equation. We want an equation linking weight, mass, and gravity. And again, pause the video, and then when you're ready to go, press play. Hopefully you've got that one. It was W equal to mg. Weight was equal to mass times gravity. This may be one you've not come across for a while. Make sure you've got that one down. Another equation we need is linking mass, density, and volume. And this time I suggest you make mass on the left-hand side of your equation. You might not be so sure about this one. The equation I was looking for there was m equal to rho v, mass equal to density times volume. You may have written this down as density equal to mass over volume, which is completely fine. It's the same equation, it's just in a different form. And this form is going to be helpful, and I've called that number 3. Last one, more of a maths equation, an equation for the volume of our cylinder, which is linking volume, area, and height, v, a, and h. Feel free to write that down now. Okay, somewhat predictably, number 4, that's V equal to AH. Okay, now what we're going to do, the reason we're doing this, we're kind of collecting ingredients, if you like, to bake a cake. And that cake is going to be an equation which will explain what you can see on the screen. Now, somewhat sort of ironically, I'm going to cause this picture to disappear. Okay, so just remember, we're trying to prove that the deeper we go, the greater that height H, the more pressure we get, because that's what's going to shoot our liquid further and further from the base of the cylinder. So we'll say bye-bye to our picture, and we'll get down to the sort of slightly difficult bit. Now, don't worry if you don't follow this entirely. Really, the most important bit for me is the destination. In this case, usually it's not. However, I really want you to see the process that we go through to see if you can work this thing out. Okay, so first thing we're going to do is we're going to take our equations 1 and 2, and we're going to combine them. What we're going to do is we're going to substitute number 2 into number 1. Now, this is probably the trickiest bit because the symbols are a little bit different. So what I'm going to remind you here is that weight is a force. Okay, so what I want you to do is take that weight and your equation number 1 and replace the force with the equation for weight. Give it a go and then press play when you're ready to go. Okay, hopefully you've tried that. You may have something completely silly. Don't worry, score it out if it's not mustn't match what I've got. Okay, this is the hardest bit because the symbols don't quite match up. What we said there was we're going to take any force in equation 1 and replace it with the weight. Okay, now in other words, what we're saying is that F and W are the same thing. The force is equal to the weight. Well, weight is a force, so that makes sense. Okay, and the end result is that P is now going to be equal to mg over A. Pressure at the bottom of this liquid is going to be equal to m times g over A. Well, that makes sense, right? Because if I added more mass, we're going to have more weight, and therefore more weight, more force, more pressure. Okay, so we're using the weight of this column of liquid to drive our pressure. The next one hopefully is a little bit simpler. What we're now going to do is we're going to take number 3 and we're going to sub it into number 5. That's our new equation number 5. Okay, so this time look for the symbols which are common. Okay, you notice that equation number 3 is for mass. So what you want to do is replace the equation for mass, that number 3, into mass in equation 5. So let's just try this one. Hopefully a bit clearer. Don't worry if you're shaking your head saying, I have no idea what's going on here. Don't worry, just trust the process. We notice here in our equation 5, we have mg, okay, on the top there. Well, I'm going to replace that m with rho v. So I've got rho vg. It's getting really complicated now and horrible. Don't worry, it's going to get simpler. Okay, so we've now got an equation which says pressure is equal to rho v over A again. It makes sense. If I had more liquid, it would have more pressure. That makes sense. Also, more density would have more pressure. So we're introducing different variables here. The last one, substitution we're going to do, don't worry, almost there, is to substitute number 4 into 6. Now this time, hopefully you've got the hang of it. Okay, you want to find a symbol in 6, which is the same as the symbol in 4, and simply substitute in. Okay, hopefully you've had a go at this. Let's try it. Did you get that? No worries if you didn't. We've substituted V equal to AH. We've got rho AHG over A. This is becoming disgusting, isn't it? And it's really not a nice equation to look at. However, we're going to just make it a bit simpler. We're going to cancel something. Hopefully you can see what we can cancel. You should be shouting at your screen right now. It should be able to cancel A because we have an A on the top and the bottom. Okay, we cancel those A's, it becomes a bit simpler. We arrive at the final equation, don't worry, last one, which is that the pressure at the bottom of that column is equal to rho hg. Got rid of the A. Now let's just take a second to think what that means. It means that the pressure depends on the height or the depth of this column. It means that the higher we go, the bigger the column, okay, the higher the column of water, or the deeper we go into the water, it means that our pressure is going to increase. And it's not only going to just increase sort of in a random way, it's going to increase linearly. Okay, if I double the depth, I'm going to double the pressure there. Okay, now this equation, P equal to rho hg, sometimes called rho gh, doesn't matter, is the equation that we need to get to. So no worries if you didn't get any of this stuff, okay? Don't worry about it. Simply take the equation and we'll write it down. Tell you what, we'll go on to the next slide. We'll see it here. We've modeled our water as a column, and we've said that the pressure in the liquid is given by rho hg. Now this time, our rho is the density of the liquid itself. Okay, h, again, I'm a bit worried about this height. H is the height or depth. Okay, it's really about going deeper into there and think about the water above you at a certain point. Okay, and G is our gravitational field strength. Okay, pressure equal to rho hg. It says that if I use a higher density of water, higher density of liquid, I should say, I'll have greater pressure. It means if the liquid has a greater height, I'll have a greater pressure. And it says that if I go to a different planet where, for example, gravity is stronger, I will have a greater pressure. This is really our equation we'll use. So let's recover a little bit and try to just make sure we're kind of confident with using the equation. Let's imagine I asked you to calculate the pressure at the bottom of a swimming pool, which has depth 2.4 meters. We can assume that the swimming pool's on Earth, and we can assume that the density of water is 1,000 kilograms per meter cubed. So let's get our confidence back. You may have not enjoyed the equations, but you can hopefully use it. Pause the video, try the question, and then we'll see the answer. Okay, let's go for it one final time. We're using pressure equal to rho hg. Okay, we know rho is 1,000. We know h is 2.4. Now, the one that you might not have known is what g is. And I'm being lazy after all that work with equations. I'm going to say that g on Earth is equal to 10. And so therefore, what I'm going to say is rho is equal to 1,000 times 2.4 times 10. Okay, multiply them together, and we're going to get 24,000 pascals. Remember, we've not talked about units in this video. Our pressure is always given in pascals. Okay, well done. You got there. Don't worry about all that deriving stuff. It's really just a glimpse into where this all comes from. If as long as you're comfortable with the equation, what these numbers mean, and have an idea of where they come from, I've done my job. Okay, if you're in my class, you should be getting on to do a few more questions to practice your use of pressure equal to rho hg.